thank you, Pierre, for the introduction, and thank you to the organisers for the opportunity to speak to you today in this beautiful conference centre and, well, beautiful concert hall. I don't think I've ever given a talk in a concert hall before. So I'm going to talk to you this afternoon about what challenges remain on the roadmap towards the redefinition of the SI second. We've heard a number of speakers allude to this redefinition, but there are a number of things that stand between us and that. So I thought I'd start by just reminding you how the second is defined today. So it's the second at the moment, and since 1967, has been defined in terms of the ground state hyperfine splitting in the caesium-133 atom. And that definition is realized today using cesium fountain primary frequency standards. The best of these standards have a uncertainty now reaching as low as the low parts in 10 to the 16 level. And these cesium fountains are used both to contribute to global timescales, TAI and UTC, that's International Atomic Time and Coordinated Universal Time. And they're also used to contribute to the physical realizations of UTC maintained by national metrology institutes. So in the UK, that would be UTC MPL is our timescale. Here in Canada, it would be UTC NRC. So the next generation of clocks, though, will be based on optical rather than microwave transitions. And the improved resolution of these optical clocks is essentially derived from their much higher operating frequency. So all other things being equal, the instability of a clock is inversely proportional to the quality factor of the transition that we use as the reference for that clock. And that means the ratio of the transition frequency to its line width. Now, if we go from the microwave into the optical regions of the spectrum, the optical frequencies are about 5 orders of magnitude higher than the microwave ones. But the line width limiting processes in those two spectral regions are broadly similar. And so what that means is that in principle, you can gain a huge improvement in instability by moving into the optical region of the spectrum. And there are two types of optical clock under development today. So there are trapped ion optical clocks. We heard about those from Eckhard Pike on Monday. And there are optical lattice clocks, which we'll hear a lot more about in the following talk. And basically, both types of clocks have made enormous improvements in both stability and accuracy over the last years. And now to the point where the best optical clocks have estimated systematic uncertainties reaching just below the part in 10 to the 18 level. And so, of course, that does raise the question, if they're 2 orders of magnitude better than cesium, this is why we're anticipating a redefinition of the SI second. And in the meantime, what we can do is we can use some of these optical clocks as what are called secondary representations of the second. So these are standards which we can use to realize the second, but whilst the current definition of the second remains, the uncertainty of that realization can't be any better than the best cesium primary standards. So in 2020, the Consultative Committee for Time and Frequency, this is one of the advisory committees that advise the International Committee for Weights and Measures, the CCTF set up a task force for the redefinition of the second to develop the roadmap towards that redefinition. And this task force established a set of criteria which we could use to assess our readiness for a redefinition of the second. And these are divided into mandatory criteria that have to be met before the redefinition can happen, and a set of ancillary conditions that should be well advanced by the time of the redefinition, but they don't have to have been completely achieved. And so I'll talk through some of the progress that's being made against working towards these mandatory criteria and ancillary conditions. And I'll do this drawing on examples from work performed at MPL, in particular in the context of the European project Robust Optical Clocks for International Timescales, or ROCIT for short, which I'm coordinating at the moment. But of course, many other groups around the world are also tackling these challenges that you see here. So the clocks I'll discuss are the two MPL optical clocks that you see here. We have an ytterbium ion optical clock that can run on either the electric quadrupole or the electric octupole transition. And we have a strontium optical lattice clock. And I've shown the current uncertainty budgets here, although of course work's continually ongoing to try and push these to even lower uncertainties. Now, I'm going to start with one of the ancillary conditions, which might seem a bit of an odd place to start. This is the high reliability of optical standards. But the reason for starting here is that if you've got a highly reliable standard, it is an awful lot easier to do the experiments that help you meet the other conditions here. So we've put a lot of effort recently into improving the robustness of our optical clocks at MPL. So, for example, we've done a lot of work on automated relocking systems for the lasers we need to operate the clocks. We've also done a lot of work on automating other aspects of operation. For example, for the ytterbium ion clock, we've now got software which will automate processes like ion loading or residual minimization of electric and magnetic field gradients. So all that we need to do now is the operator has to press a single button and then the rest happens automatically. And we've also put a lot of effort into remote monitoring and control. Here you just see some of the screenshots from the monitoring systems for the strontium lattice clock and the frequency combs that we use to make measurements on the clocks. And we've really seen a lot of dividend from the work we've put into this, because now we can monitor and, in most cases, fix problems from home. And that's really, really beneficial when it comes to running long measurement campaigns. They're definitely an awful lot less painful than they were in the past. So now I want to come on to some of the mandatory criteria, and these are all to do with assessing the international consistency of optical clocks through comparisons between clocks that have been independently developed in different laboratories around the world. And also to link, those comparisons are really important because they'll help to build confidence in the new generation of clocks and their estimated uncertainty budgets, but they'll also help us to anchor the frequencies of those new clocks as tightly as we can to the current definition of the second. And that's a really important point because we mustn't introduce any discontinuity at the point we choose to make that change in the definition. So to measure the absolute frequency of an optical clock, we use a femtosecond optical frequency comb. And basically what the comb does is it links the frequency of the optical clock back to the cesium fountain primary frequency standard. And of course, we can compare absolute frequency measurements that we make at MPL with absolute frequency measurements made in other labs around the world. And I've just shown you here a comparison for ytterbium ion optical clock and for the strontium lattice clock. And the agreement is pretty nice on the whole, but the problem is that all these measurements are limited by the uncertainties of the cesium primary frequency standards to about the low parts in 10 to the 16 level. And that's 2 orders of magnitude worse than the optical clocks. And worse, you also need very long averaging times to reach those uncertainties because it takes a long time to average the uncertainty of the fountain down. So this isn't a good way of making international comparisons between optical clocks. What else can we do? Well, we can think about using the satellite techniques that we use today to compare microwave atomic clocks in the different labs around the world, and that's how international atomic time is built up. And we have tried doing comparisons using those techniques, and I've just shown a couple of examples here. But again, the problem is these are microwave links, and that means that we need very long averaging times, and the uncertainties are limited again. The best uncertainties we've been able to achieve are at the low parts in 10 to the 16 level. So again, this doesn't match the performance of the optical clocks. Another possibility would be to use a transportable optical clock, and that's something we'll hear more about in the following talk. But within Europe, we're really fortunate in having an optical fibre network that links 4 national metrology institutes in the UK, France, Germany, and Italy. And this gives us the possibility to compare the optical clocks using the standard 1.5 microns transmission band of standard telecommunications fibre. So what happens is that the environmental perturbations on the fibre do affect the stability and accuracy of the transmitted signal. So these perturbations might come from vibrations due to traffic, or temperature changes on the fibre causing longer-term phase fluctuations. But what we can do is we can measure and compensate for those effects by returning part of the transmitted signal to the transmitter end of the fibre. And then we use phase noise compensation techniques to take out those effects. And so this kind of fibre network, so far we've reached comparison uncertainties at the low parts in 10 to the 17 level, and 1 part in 10 to the 18 is definitely possible in future using this kind of technique. So this is a really great facility available to us in Europe, which enables the comparisons on a continental scale. Those comparisons actually aren't just interesting for metrology, they're also interesting for fundamental physics, and I've just shown a couple of examples of fundamental physics tests we've carried out using this network. The first one was a test of Lorentz invariance made by comparing 4 strontium optical lattice clocks in 3 laboratories. And here the idea was that by searching for any daily variations in the frequency differences between the clocks, we could test the assumption that there was a no preferred frame of reference in the universe. And that experiment enabled us to improve by a factor of 2 on previous tests of Lorentz invariance. The second example involved a comparison of strontium, mercury, and ytterbium ion clocks in 3 labs. And here what we were doing was we were searching for variations in the frequency ratios between those clocks that were coherent across the whole network. And with these experiments, we were able to improve constraints on transient variations of alpha, especially for timescales longer than 100 seconds, where the long-term stability of the optical clocks really gives benefits over alternative approaches to these experiments. And it was also possible to interpret the results of those experiments in terms of a search for dark matter in the form of topological defects, though all we did was improve the limits on those. We didn't detect any topological defects. Then more recently, in March this year, we carried out a very big international clock comparison campaign. This time it involved 12 optical clocks in 7 different countries. We used satellite links as well as fibre links, because even though they're not as good, not all labs are linked by fibre. So this enabled more labs to participate in the campaign, including, in fact, one of our collaborator in Japan, the ytterbium lattice clock at NMIJ. They joined in this campaign too. And alongside those remote comparisons, we also made local frequency ratio measurements and absolute frequency measurements of the different clocks involved. But of course, a measurement of that scale, measurement campaign of that scale really generates a lot of data, and the analysis of that data is still ongoing, so I'm not going to show you any of the results today. So fibres, I said, are great on continental scales, but what about intercontinental comparisons? So at the moment, we have no way of comparing optical clocks in different continents at a level commensurate with their estimated uncertainty budgets. But there are some quite interesting prospects, I think, for doing these intercontinental comparisons via fibre. And I just wanted to show some of this work. We're actually very fortunate in that for the last couple of years, we've had access to a transatlantic fibre running between Southport in the UK and Halifax here in Canada. And now mostly this has been used by my colleague Giuseppe Mara for environmental sensing. So he's been detecting things like underwater earthquakes, ocean currents, and pretty much all sorts of interesting things in the two references I've shown here. But from the point of this talk, this fibre actually has indicated to us that there can be really quite good prospects for intercontinental clock comparisons via fibre. So what we did was we made an interferometric measurement of the noise on the fibre, and what we found was that it was actually much lower noise compared to a terrestrial fibre of a similar length. So the free-running instability reached something like the 10 to the minus 14 level at averaging times of a few hundred seconds. And that is actually very, very encouraging to think that we might be able to then cancel this noise. We can't do it in the normal ways because there are many, many unidirectional amplifiers on this transatlantic fibre, and we can't do what we do in terrestrial links and rip them all out and put our own special bidirectional ones in. But what modelling has shown us is that we think that the noise between two fibres in the pair is actually quite strongly correlated, and so that you could probably achieve pretty good phase noise compensation by using different fibres for the out and back paths. But at the moment, I stress that that's speculation. We haven't done the experiments yet. But I'd say I'm quite optimistic that we can achieve frequency comparisons at an interesting level using this kind of technique. So now I want to move on to another of the conditions, which is about our knowledge of the local geopotential. And we heard quite a lot about clocks and gravity and why this matters this morning. Basically, the frequency at which a clock ticks depends on the gravity potential it experiences and the velocity with which it moves. And the relativistic redshift between two earthbound clocks at rest is basically proportional to the gravity potential between them. So for clock comparisons, all we care about is the differential redshift between the two clock locations, which amounts to 1 part in 10 to the 16 per meter difference in height at the Earth's surface. But for contributions to timescales, which are international and all the clocks are at different heights, we need to know the absolute potential relative to some conventional equipotential surface W0, which is contained in the definition of International Atomic Time. And we really need to know this at quite a good level because 10 to the minus 18 clock accuracy corresponds to 1 centimetre in height at the Earth's surface. So a few years ago, we put a lot of effort into improving our knowledge of the European geopotential. We did this in the framework of a different European project called ITOC, or International Timescales with Optical Clocks. And basically, we collaborated with a group for the University of Hanover, who were geodetic experts. And we made two sorts of measurements. So the first were geometric leveling measurements. So these are like surveying measurements. And so as a result of those surveying measurements, we know the height differences between the clocks within each individual lab to maybe 1 to 3 millimetre level. So that's adequate for supporting the local clock comparisons. But the problem with leveling measurements is that the systematic uncertainties accumulate over longer distances, and they build up to something like the decimeter level over distances of about 1,000 kilometers. So that's no good for the remote clock comparisons. The uncertainty is too large. So what we did was the Hanover guys made a whole set of gravity measurements. So that involved at least one absolute gravity measurement at each clock site and a whole set of relative gravity measurements around each site. And then what they did was they took all those gravity measurements and fed it into their existing gravity database, and then they combined it with topographic information and a global geopotential model to calculate a new European gravimetric quasi-geoid model. And the accuracy of that model was good to something that corresponds to about 2 parts in 10 to the 18 in clock performance. So this was a really big improvement on what came before, and it also had the advantage that it meant we were all using values that were referenced to a common equipotential surface. So it brought consistency to the values we were using within the European metrology labs. They also did a little bit of work on modelling time-varying effects to give us an idea how large these were. I should stress they can be modelled at the level of the clock accuracy, but for example, the maximum time-varying effects between MPL and PTB are something like about a part in 10 to the 17. So for the highest accuracy measurements, we do need to take into account those effects. Okay, so another important criterion in the mandatory list is that optical clocks must make regular contributions to UTC, or TAI, as secondary representations of the second. It's no good redefining the second if the clocks aren't in a state where we can actually use them for timescales. And the way in which they contribute is similar to what's done today for primary frequency standards. So basically you use the optical clock to calibrate the frequency of one of the commercial clocks that contributes data on a regular basis to TAI, or to the BIPM for computation of TAI. And we do this by assuming that once we've corrected for all the systematic effects in the proper way, then the clock runs at what's the frequency specified in this list of recommended values of standard frequencies, which is maintained by the BIPM and published on their website. There are some administrative hurdles you have to overcome. So for first submission of a new optical clock to contribute, you have to gather calibration data over an extended period, and you also have to have a peer-reviewed publication that describes the operation of the clock and the evaluation of its uncertainty budget. That material has to be reviewed by the CCTF working group on primary and secondary frequency standards before the clock can be used for steering. And right now we're in the process of gathering and preparing all that data from our strontium lattice clock for our first submission. But there are a few optical clocks already contributing periodically to TAI. So I mentioned this list of recommended frequency values, but how are those derived? Well, basically they are computed by the CCTF working group on frequency standards based on the worldwide body of clock comparison data. And this was really quite a straightforward job, whilst the only thing that was available to the group was absolute frequency measurements, because you just take all the measurements for a given standard and take a weighted mean, and that's your answer. And so, but then by 2015, the problem was that direct optical frequency ratio measurements had also been reported. And that makes the situation a lot more complicated because you can't treat each of the standards in isolation when you're considering the available data. So basically methods had to be developed for considering this kind of over-determined set of clock comparison data. And the methods are based on they're pretty much the same methods that are used, a least squares adjustment procedure that's similar to what CODATA used for the adjustment of the fundamental physical constants. And these methods were first used to update the list of recommended frequency values in September 2015. So in that least squares adjustment, all the data is treated as frequency ratios, so there's nothing special about the caesium atom in that sense. We just compute the absolute frequencies as the last step. And importantly, correlations can also be included in the analysis where they're known. And that's really important to avoid biasing the frequency values and underestimating the uncertainties. Nevertheless, in 2015 and 2017, when updating the list, the working group did not take into account correlations. And that was really bad because the correlations can be quite significant. In particular, correlations can come from common data. So if measurements are made at the same time, or even if measurements are made against TAI several months apart, because the same fountains contribute to TAI month after month, that can lead to very strong correlations. But finally, based on these guidelines that I just showed you that were written by myself and a colleague from INRIM, the working group in their latest adjustment did include correlations, calculated no less than a grand total of 483 correlation coefficients between 155 input data points. And that was worth it, actually, because it did significantly affect the emerging frequency values compared with what happened without correlations. And as a result of this analysis, 6 secondary representations of the second now have uncertainties below 2 parts in 10 to the 16, which means that if they can achieve the same uptimes as the microwave clocks, the primary standards, they can contribute to TAI with a similar weight. Okay, so then just finally, I want to talk a little bit about using optical clocks to steer UTC-K timescales, so like UTC-MPL, because we did a first experiment of this recently. And so this again happens in a similar way to primary standards. So with the caesium primary standard, we typically steer 3 times a week at MPL. That's because it takes us 3 days to average down the caesium fountain noise to below the noise of the maser, that we then steer using an external frequency offset generator. But the optical clocks have better stability than the maser for all timescales, so in this case we opted for hourly steering. And then to see how we were doing, we just compare our prototype optically steered timescale with our real timescale, UTC-MPL. And of course, to do this, we have to automate all our data validation and steering corrections, because it would be pretty boring having to sit there and do it manually every hour. So this is what we see when we start doing the comparison between the prototype timescale and UTC-MPL. The problem is we're doing this experiment blind, and we don't know, is that variation of several nanoseconds due to the prototype timescale or to the real one? But after a week, we get data in from the BIPM in what's called rapid UTC, or UTC-R. And this is a more rapid computation of UTC, but it's usually in pretty good agreement with UTC. And we were pretty happy when the first UTC-R came in, because what we saw was that the difference between UTC-R and UTC-MPL was almost the same as between the prototype timescale and UTC-MPL. And so the residuals basically tell us how stable the optical timescale is, because UTC-R should be better than any individual timescale. And so that we then carried on for another week and saw some more wiggles, but again, when UTC-R came in, we were seeing pretty nice agreement again. But good things come to an end, and then things didn't look quite so nice for the next couple of weeks. We saw an unexpected phase step in the output of the frequency offset generator. We're still trying to understand the origin of that. And unfortunately, we let through 2 bits of bad optical clock data, and therefore steered the timescale wrongly. But because we could see we'd done that, we then tried to apply a manual correction to take out the worst of it. So with all that thrown in, the instability of the timescale did get a bit worse in the last part of the campaign, but it still remained within 1 nanosecond of UTC-R, which, to set that in context, we typically keep our current timescale within about 5 nanoseconds of UTC. So this is an improvement on that. So with that, I'm going to round up. Hopefully I've convinced you progress is being made on the roadmap towards a redefinition of the second. And there's still a lot left to do, but I think we can be quite optimistic that we might make that target date of 2030. That's the preferred scenario for the redefinition. And with that, I'm just going to finish by thanking my colleagues in the Time and Frequency Department at MPL, in the ROCIT Consortium, and on the CCTF Task Force for Redefinition. Thank you for listening, and I'd be very happy to take any questions.
Thank you, Helen, for a very clear and interesting talk. So now we can take a few questions, and again, students will get a little card if they ask questions. So,
if I understood correctly, I think you mentioned that there are time variations in clock comparisons between MPL and PTB at the 10 to minus 17 level. Could you elaborate a little more what's going on there?
Yeah, the dominant effect there is solid Earth tides, causing just gravitational, the gravity potential difference to vary between those two sites, and that's the level of that. There are a whole host of other effects, but they're smaller.
I guess next question by June.
Helen, thanks. Can you comment on the time scale steering?
Mm-hmm.
Optical clock is far better than the hydrogen maser. And shouldn't we have a laser that's the one that's the local oscillator that's being steered by your optical clock?
Yeah, absolutely. This would be like the next step beyond what we've done now, because we need it. But the challenge there is you have to have something that runs continuously, because to me this was the big education. Like when we tried timescale steering, I'm used to thinking about frequency.
Right.
And if your frequency standard goes wrong, you can just stop it for a while and then restart it. But if you do that with a timescale, you obviously lose track of time. So, yeah, you have to have a system, or at least an ensemble of systems, where something is always running continuously. But I think, and probably you were involved in it, but there was some work done at NIST and JILA, right? On a first attempt at like steering a timescale that involved an optical local oscillator rather than a maser.
Silicon cavity.
Yeah.
You have to operate all the time. Indeed.
Yeah.
Hi.
Okay, so I've got a question, but I'm not sure exactly how to ask it, so I'm going to ask you to tell me how I should ask this question. So eventually we're hoping that there's going to be a redefinition of the second, and leaving apart questions about what atom it's going to be, or God forbid if it's going to be a collection of atoms, there's the sort of the mise en pratique part of where in the gravitational potential you are. So now there's attached to caesium, and its mise en pratique is the specification of the geoid. But we now know that sea level is changing pretty rapidly. The ice caps are melting. The distribution of mass in the Earth is changing. What can we do to define what we mean by a second in a way that's meaningful at the level that the clocks are going to be performing at in 2030?
Okay, so I think so the first part, I don't think the gravity matters for the definition of the second, because that's done in the local frame of reference. What it matters for is timescales.
Yeah.
Yeah. So I completely agree that all these things are going to be a problem eventually, and that's why we have to do measurements of the type we did with the Hanover guys, and you will have to repeat them periodically because of changing sea levels and all these things. I think the limit is going to come from the unpredictable effects at the Earth's surface that we can't model, which are probably somewhere between the 10 to the minus 18 and 10 to the minus 19 level. And so really the only way I can see of getting around those is to take your clock and put it into space. But that's obviously very difficult.
But so do you think that's realistic? Say, set the thing at a Lagrange point or something like that? Does that sound like a good idea? I mean, are we going to know where that is to within?
The Lagrange point might be a bit extreme.
Well, where would you like to put it?
Well, I mean, even just like taking it away from the Earth's surface will help a lot, because, you know, the variations fall off as you take it further away. So I don't know whether you need to go as far as the Lagrange point, but to me the biggest challenge is technical, of building a clock that will actually work that well in space.
Yeah, but there'll be some orbit height, but that orbit height measured relative to what?
Well, relative to the same equipotential surface, I guess.
Which may be
But-
changing.
Which will be, yeah, no, that's true. So it's the definition of TAI that you need to.
I
you need
guess.
to
I
think
don't know.
about.
That's why I'm asking you, because I
No,
don't
no,
know.
the definition of TAI is where that potential value appears. Yeah. It's a good question.
But it's not an easy question.
No,
it
no,
seems.
it's definitely not. But I'll be pretty happy when we get to that limit.
Of course, I might be dead by then.
Thank you. We have a question from down there. No?
Bill
No?
asked it.
Ah.
Did you have a question? Yes.
Okay.
Hi, nice
Hi.
talk, by the way. I wonder, so you mentioned there will be a fiber, there is a fiber in the Europe continent that connects 3 labs.
Mhm.
And I wonder, you said there will be phase noise cancellation by reflecting just
Yeah.
redirect the laser back.
Mhm.
I wonder if there's any fundamental limit to the goodness of this method.
Yeah, absolutely there is, because in the end you're limited by the round trip time
Yes,
in
it will be very
the
long and-
fibre.
Yeah.
So it's not a serious limit at the level we need to cancel the noise, but yes, but what you could do is, if necessary, you can break a long link into shorter spans, and you cancel each stage of it, independently, if you get close to that limit.
Increase the bandwidth, the
Yep.
noise cancel. I
Yep.
see. Thank you.
Are there any other questions? Yes?
You had a lot of long fibers, and so there are a lot of repeaters, and you use these fibers for frequency comparisons. My question is just why wouldn't these repeaters cause problems to your frequency comparisons?
So the repeaters, well, okay, in this case, they might. For the intercontinental fibre, we haven't tried that yet. But normally what we do is we have special repeater stations that we build ourselves, and all the amplifiers are custom bidirectional ones as well. So we're not just using, in the European links, we're not using the standard stuff that you just find in a telecoms network. We have to bypass that. And it's a fully optical link, I should make clear as well.
Okay, thank you.
Okay, we have one online question, and I think that will be the last question for this talk. So how well is the actual path of the transatlantic fiber known, and what would be the Sagnac uncertainty limit over that link?
Sorry, what was the second part there?
The Sagnac uncertainty.
So I remember asking my colleague exactly how well the path of the fibre was known. Can't actually remember the answer, but it was surprisingly well to me.
Okay.
I'd have to go away and check that. The Sagnac, I'm not sure. For the European links, it's less than below the part in 10 to the 18 level. But I haven't calculated it for a transatlantic one yet. But I guess it would be, given that the path is known reasonably well, I guess it wouldn't be a big limit.
Okay, thank you. And let's thank Helen again.